Hello everyone. My name is Celal Zifci. I work at Google New York office and I will be presenting the paper titled De-Flake Your Tests, Automatically Locating Root Causes of Flaky Tests in Code at Google. First, I'll begin by expressing the problem. So regression testing is a pretty common practice in the industry and it ensures that modifications to software does not break existing behavior or functionality. So in practice, regression tests are assumed to be consistent and deterministic, meaning if you run the regression test suite on the same version of your software system, the results should be the same. They should either pass or fail. However, in practice, there are tests called flaky tests that are not like that. Sometimes they fail and sometimes they pass at the exact same version of the software. So flaky tests are the root cause of considerable portion of test suite failures according to the reports by academicians and practitioners. They are pretty hard to debug because they are not easy to reproduce because they're not deterministic. And they waste a considerable amount of time because they fail on code changes that are unrelated to the current modifications that a developer is working on. And finally, there's a decreased perception of trust on regression test suites due to flaky tests, and developers start ignoring the results of their test suites, which is very dangerous because it may actually mask real bugs in their code bases. So how do people deal with flaky tests? Sometimes they run them several times, and for example, we also do this in Google. Sometimes we run them a certain number of times. If one of the runs pass, then we consider a test to have passed. Another way to deal with them is to ignore them. For example, if you have a full test suite, you may create another one that is called for flakiness, and you may actually move some of your tests in and out of this suite as they become flaky or not flaky. Obviously, this is a manual process, and the contents of each suite will get out of date very quickly over time. So overall, the ideal solution is to fix the flaky tests as quickly as possible. So now I'm going to explain our algorithm to help debug them and the tool that implements it called Flakiness Debugger, FD for short. I'll start with an example. So in this example, if you look at line 7, between lines 7 and 12, this is a method that returns 0 or 1 randomly. And it uses the built-in random number generation in Java. And so this is, let's say, the production code. And now I'm going to show you a test code which actually tests this. So this test asserts that the random 0 or 1 method always returns 0, which is obviously a bad test, but in reality, there are tests that are pretty similar to this. So 50% of the time, this test is supposed to fail because it will potentially generate 1. So what we do in Divergence is we run the test many times. We find passing and failing ones, and we compare passing ones with failing ones. So, and we find the first point of divergence. In this example, lines 7 to 9 are common between passing and failing runs. On the left, there's a passing run where it returns 0 at line 10, and on the right, there's a failing run that returns 1 on line 12. So these are the divergence points. And FD, the Flakiness Debugger tool, produces a report that looks like this. It shows common lines as gray, first passing line as green, and first failing one as red. So hopefully when people look at this report, they will understand where flakiness is being caused. So now I'm going to talk about some case studies. In our first case study, we found 83 historical flaky tests in C++ and Java. These tests are all fixed already manually by developers without any help from any tool at all. And we also know how they fix them because they attach the fixes to the issues. Now, what we did is we went back and ran Flakiness Debugger on the versions of those tests that they were flaky at, basically before they were fixed. Then we recruited 2 independent developers that work at Google that are not in the teams that own any of these flaky tests and that are not aware of the fix. They did not see the fix. And we asked them to categorize the reports in 3 classifications. First is useful exact. In this classification, flakiness is due to the exact lines pointed to by the FD report, and it can be fixed by changing those lines exactly. Second one is useful relevant, where flakiness is relevant to the lines pointed, but they should be fixed in another location. For example, maybe some RPC call timed out and the timeout is defined in another file. Finally, not useful. This classification is for reports where developers just couldn't figure out what the report was trying to tell them. Here are the results. So what we look at is useful exact and useful relevant. So the two developers basically said the same 68 issues in total out of 83 were useful in one way to actually fix the root cause. And in 15 of them, they found the reports to be not useful. We later looked at these 15 and found that 4 of them could actually have been useful if the developers were experienced in the domain that the test belonged to, and 11 of them were due to test terminations by the test runner because the tests were taking too long. Therefore, they were just terminated at random points in code execution, and the reports were just not useful. In another case study, our case study 3, we used Google Issue Tracker. So this is an internal issue tracker that we use at Google, and we basically found 300 issues already manually opened by developers so that they fixed flaky tests in their test suites. What we did then is we ran flakiness debugger on them and produced reports for each of them, and we commented on those issues automatically to say that we have a report that might help them fix it. 166 of these issues were later fixed, and we asked the 150 unique developers that actually fixed them to give us feedback whether they found FD reports useful, and 18 of them responded. This feedback was very positive. They basically said they liked the reports and they were actually useful, and we didn't receive any negative feedback on this case study. Finally, in case study 4, we asked developers an open-ended question saying, did you find FD useful at all? So after this, we had some positive feedback where developers said it actually helped them identify the problem faster and the report was useful and they understood what it was trying to tell them. In another set of feedback, we received some negative feedback, especially when we looked at the details. These were for useful relevant type reports where developers expected the report to be exactly where the problem is rather than where they show up. So they gave us negative feedback about that. Third, we got negative feedback about some usability aspects. Some users didn't understand what the tool was telling them without reading the documentation. They didn't like the presentation of the tool or reports and so on and so forth. And finally, a few users gave us feedback for improvements, such as instead of telling them where the problem was, they also wanted us to give them how to fix it, what semantically what it meant, like why the test was flaky. In summary, we presented a novel technique to find root causes of flakiness in code. FD reports were found to be 82% accurate based on a case study of 2 developers. Based on our surveys, developers are not motivated to fix flaky tests unrelated to their current code changes, and they were positive on the integration of these reports into their relevant workflows. Finally, some developers found these reports hard to understand. Some expected automatic fixes without them having to do anything, and some others wanted them to explain how to fix them as opposed to just where flakiness is caused by. This is our talk, and thanks for listening.